Alright, so we're about to dig into the nuts and bolts of plate tectonics. We'll start with the spreading of the seafloor. So in this video we'll examine the idea of mantle convection as a mechanism for continental drift, the missing mechanism that Wegener couldn't find. Then we'll describe evidence that the seafloor is in fact spreading, and then we'll explain the connection between seafloor spreading and hydrothermal vents. So if you recall a few videos ago, our poor friend Alfred Wegener died suddenly in Greenland. He couldn't figure out what was actually driving plate tectonics. The idea he proposed, this sort of pole fleeing force, no one really bought it. It didn't really make sense that the rotation of the Earth could really fling the continents farther away from themselves and help this early Pangea, where all the continents are locked together, come into the current position of the continents. So this left plate tectonics without a mechanism for quite some time. So even though there were potentially compelling parts of Alfred Wegener's idea of continental drift, the lack of mechanism really prevented it from being considered seriously. Several decades later, though, Arthur Holmes proposed this idea that you could have mantle convection the same way you have convection in a pot on the stove. So if you've ever been to a hot pot restaurant before, you see the center of the pot is boiling. There's bubbles coming up because they're right under the heat source. And that creates what's called convection here, where you have updrafts of less dense, warmer water, downdrafts of cooler water that are coming in to fill the void. So you have this circular motion develop because of this heat gradient between the burner and the room. So the same thing can happen in the mantle. This is the proposal for mantle convection. Is that we know that the core has all of this heat attached to it. We know the surface of the Earth is cool, and we know space is really cold. So Earth is losing heat to space. And that should drive a similar type of convection where the mantle is slowly flowing up, exchanging heat with the crust, gliding down here, and then sinking back down to the lower core. And then in doing so, it drags the continents along. So you have this continental block here, let's call it Pangea, and then because the mantle is diverging here, some goes left, some goes right, it breaks the continents apart. So this idea of mantle convection seems to fit with at the time, the new results of ocean bathymetry. You can see this mid-ocean ridge system over here. It basically doubles down on the fit between South America and Africa, for instance. You can see the symmetry here reflected in the mid-ocean ridge, which is cutting right through the center. So it makes sense if there's some plume of mantle coming up here, that could really be causing the continents to be pushed away, essentially. And there's other evidence that supports this idea, or at least the main points of it. This is sort of the era that radioisotopes were first being understood, and this idea that you could date different parts of our surface was becoming more popular. And so what people realized was that the age of rocks on the continent, of continental crust, was a lot older than the age of the ocean floor. So this is a map of the age of different regions across Earth's surface, going from extremely old, 3 billion years, to 3.5 billion years old. You can see the Jack Hills here in Australia. We talked about those before. But there's sort of other parts of Earth that are similarly old. And then there's parts that are very young too. But the youngest parts of the crust are around 0 to 50 million years old. It turns out, from rocks recovered from the bottom of the ocean floor, most of the ocean crust is 60 to 80 million years old. The oldest part of the seafloor near the trenches is around 200 million years. And then the youngest part of the seafloor was found at the mid-ocean ridges, around less than 20 million years old. So if you think about where that spans in terms of the age of the continents, we're down here in this red or this orange color. The oceans are much younger than the continents. So that age dating seemed to support the idea that the ocean floor was sort of rapidly being generated, and that could be responsible for the breakup of a Pangea in the past. To really confirm this, though, additional evidence needed to be pulled in, and one really lucky find was this observation of magnetic anomalies on the seafloor. This is a bit complex, so I'll go through it kind of slowly. So previously we discussed how Earth's magnetic field protects us from the solar wind. This is originating from the outer core, this sphere of molten iron that's constantly flowing and generates this magnetic force field that surrounds our planet. Now usually, or at least today, the magnetic north is aligned towards our geographic north pole. This is sort of the direction of flow around the magnet. But sometimes, and this is a mystery that we don't really understand, this reverses. So magnetic north will actually be pointing south. We know this happens because the orientation of the magnetic field is recorded in rocks that are cooling during that time. So when lava erupts, it slowly starts to cool, and as it cools, there are these minerals such as magnetite that are sensitive to Earth's magnetic field. They form, and while things are cooling down, they start to align with magnetic north. So we can go and we can look at rocks, we can date them with radioisotopes, and we can see which direction they're pointing to see where Earth's magnetic field was at that time. So going back to the mid-ocean ridges, what was found was that there are these parallel magnetic reversals stemming from the mid-ocean ridge system and going outwards, towards the continents. So what was observed was that there would be these regular reversals both to the left side and the right side of the ridge. So let's say the center of the ridge, right on the ridge axis, let's say that's a normal magnetic period where magnetic north is geographic north, but then there's a reversal period where magnetic north is pointing south. That was observed both on the left-hand side of the ridge and at the right-hand side of the ridge at similar distances from the ridge center. There'd be another reversal, so now we're back where north is north again, on both sides, reversal, normal, reversal, etc. What's striking about these parallel observations to the left-hand and the right side of the ridge, it suggests a model where the new material, new ocean floor is formed on the ridge and then pushed outwards away. So the new material takes its place, and therefore it's recording these magnetic reversals on both sides of the ridge. So by dating magnetic reversals with rocks on land, we know exactly when these reversals happen. So that became a way to basically convert these stripes on the ocean floor to a sense of age. How old is different parts of the ocean floor? And this is the result of global surveys of magnetic anomalies converted back to age. What you can see here is the youngest part of the ocean crust is found on the ridges themselves. This is basically showing that new crust is made at the ocean ridges, and it's aging as it's pushed away towards the continents. You can see the oldest crust is furthest away from the ridges. For example, this area of the Pacific is around 150 million years old. Look at how far away it is from these Pacific rise over here. There's a couple bits of even older segments in the deep Mediterranean, for instance, that are just isolated from any production of new crust on any ridges around there. It's sort of an enclosed basin. So after new crust is formed in a ridge, it's sitting tall. It's only 2,500 meters deep as opposed to 4,000 meters deep. It's relatively hot because it's just been formed from magma coming from the mantle, and it's young. It's just been formed. So as that piece of crust ages, it becomes more dense because it loses heat. So it loses heat, becomes more dense, and it starts to sit lower in the mantle because of isostatic readjustment. More dense things will sink lower into the mantle, and that's why you have this decrease in height, from the mid-ocean ridge axis out away from the ridge center. And so this causes a very noticeable difference in the way that different ridge systems look. For instance, in the North Atlantic, the mid-ocean ridge is very narrow here because this is a slower spreading ridge. You have new crust forming here, and it's not moving that far before it starts to cool down and starts to sink more, and therefore you have this really sharp rise here. In contrast, the fastest spreading ridge today is in the East Pacific Rise, and what you see here is that you have this gentle slope, and that's because the ridge is producing so much ocean crust that it's cooling slowly as it's being moved away, and so you have a gentle decline because the cooling process is happening at the same beat as the production of new seafloor that's pushing it away. So this is why you have different shapes for fast spreading ridges and slow spreading ridges. So from this discovery of magnetic anomalies on the seafloor and this age mapping of the entire ocean floor, this is transitioning this idea of continental drift, that the continents are flying apart from these unknown reasons, into something that will become the theory of plate tectonics. Essentially, you have this heat source from the Earth's core. It's diffusing through the mantle and then out into space through the continents. And as it's doing so, it's creating these convection currents in the mantle. They're moving around something like this. As they rise towards the crust, they have to diverge. And then as they diverge, they're pulling some of the crust left of the ridge, some of the crust right of the ridge. And that's creating an opportunity for new mantle to come up. As it comes up, it basically melts because there's less pressure. and then it forms solid crust, and that's how new ocean crust is born. This process eventually, ends in deep ocean trenches. That's where the oldest seafloor is, and that's where seafloor is essentially destroyed and returned back into the mantle. And we'll look at that in a little bit more detail later on. So this is sort of how seafloor spreading fulfills this missing part of continental drift. Essentially, we have mid-plate rising of a asthenosphere mantle to create new crust due to convection. And then this produces new oceanic crust at mid-ocean ridges that then splits apart to the left and to the right. As that crust is pushed away from the ridge axis, it starts to cool and contract, becomes more dense, and so it sits deeper into the mantle. That's why you have mid-ocean ridges that are standing taller than abyssal plains. Abyssal plains have seafloor that's old and cold and it's low. And then finally, we have that crust being subducted in the deep ocean trenches. That's sort of the end of the line for this conveyor belt. So this results in a young ocean crust compared to the continents because you have this constant generation and then recycling, or this removal of old ocean crust. And it's changes in the rates and potentially the location of these spreading centers that can cause continents to drift and change direction, to come apart and come together again. So the other exciting thing about mid-ocean ridges is this is home to most of the ocean's hydrothermal vents. You can see this map is showing where known hydrothermal vent locations are. There's essentially two locations where they're found. One is mid-ocean ridges and the other is ocean trenches. But you can see here in the fast-spreading East Pacific rise, look at how many vents have been discovered compared to the North Atlantic. Here, this is a slow-spreading ridge where hydrothermal vents are still present, but they're less common. So this is what they look like in motion. These are really crazy, complicated places. No two vents are exactly alike. You have this superheated water coming out. It's about 300 degrees, and on Earth's surface this would boil, but because of the pressures of the ocean, it's kept in a liquid phase. And you can see, this dark color is showing all the minerals that have basically been dissolved, and they're reprecipitating as part of these chimneys, or they're being spread out to the ocean further. Here's another vent. You can see that these black smoker chimneys are really coming and pumping out all these metals out into the ocean. And here's just one more for good measure. These are all three black smoker type vents, but this one you can see has a big ecosystem. I think this one is called crab spa. You can see the shrimps, you can see the crabs. Each of these organisms has some kind of symbiotic relationship with bacteria that allow it to take advantage of the energy source that this mixing of geological fluids with seawater allows. This is a pretty incredible source of life and energy that's totally decoupled from our sun, for instance. So how do these hydrothermal vents work? Well, they pull in seawater essentially from the side of the mid-ocean ridge. That's sort of where seawater percolates into this basalt. There's pores in the rock, it pulls in, and then as it moves and percolates closer towards the actual spreading center, towards the ridge axis, it gets some of this heat from this magma chamber below. This magma is probably around 1200 degrees Celsius. This diffuses upwards, and so there's this reaction zone where the seawater that's percolated into the rock is around 400 degrees C. At that point, things get really hot. That seawater gets very buoyant and starts to rush upwards. And it comes out of these chimneys as these black smoker plumes. They're dark colored because they have all this iron, manganese, and other metals that are basically dissolved in them. And then they keep rising up because they're buoyant, and eventually they hit some plane where the density of the fluid is the same as the density of the surrounding seawater, and they kind of level out. So this is what's called a buoyant plume. And then these sort of will just ride the currents. And so in this case, if the currents are going left, that's where the plume is going. And during this time, some of these elements that are in the plume become unstable. They precipitate out and produce these metalliferous or metal-rich sediments down in the seafloor. But all of this whole area is a place for life to thrive. So not only that, this is a big source of some elements that are nutrients for the rest of the ocean. So one example here is iron. Iron is coming out of the hydrothermal vents on the East Pacific rise. This over here is a transect from Peru over here to Tahiti. This is actually a cruise that I was able to take part on, so I was on this cruise for 2 months, helping to measure the chemical parts of seawater. So you can see this is the sort of a section of iron concentration here. You can see this big bullseye of high iron coming out of these vents and basically riding the currents to the left with that seawater. This is a big source of iron that's needed by phytoplankton in Earth's surface. And you can see here in the Earth's surface, there's not very much iron here. So these hydrothermal sources could be a really big deal in terms of providing the ocean with a source of this nutrient that's hard to get otherwise. So the main points in this video, we're looking at mantle conduction as a mechanism for continental drift. This is relying on the fundamental heat gradients between Earth's core and Earth's surface. And this provides a way that the ocean crust can be split apart for new mantle to turn into ocean crust at the seafloor at mid-ocean ridges, and then for those ridges to keep being pulled apart so the new seafloor can be made. The evidence for this largely comes from both the young age of the ocean crust and these observations of parallel magnetic stripes on the seafloor. This is really key to showing that the Earth is producing ocean crust and pulling it apart evenly to the left and to the right. And finally, we talked about how this seafloor spreading creates this unique ecosystem in hydrothermal vents, how it allows seawater to come in, become rich in different nutrients and different elements, and that provides a source of chemical energy and nutrients for life that lives in the ocean itself.